what happens if we deviate from the ideal gas law. So really it's like real versus ideal gases. And we can assume gases will behave ideally unless they give you enough information that it's like, yikes, maybe this won't work. So all real gases do not behave ideally under high pressure and low temperature. So I could probably end this lecture right now as long as you come away knowing that gases do not behave ideally when they're under high pressure and at low temperatures. I always say gases like to live where I live. I don't like a lot of pressure and I get really cold, so I don't like low temperatures. But basically, at high pressure and low temperatures, the ideal gas law does not make accurate predictions. And this is probably the most important slide from the whole lecture. Now, the rest of the lecture is going to kind of show you some examples of why that doesn't happen. So you don't really have to do a lot of that math or anything. The most important takeaway from this is that under high pressure and low temperatures, gases are not going to behave ideally. So this just kind of shows you that PV over RT versus pressure for 1 mole of an ideal gas. So notice the nice little behavior of our ideal gas, okay? But notice then 1 mole of different gases at constant temperature. Notice what is happening when we increase the pressure. Our gases behave less ideally. So notice the deviation. And so these gases, methane and CO2 and helium, are only going to behave ideally at pressures below about 5 atmospheres. So the ideal gas equation assumes that molecules don't have their own volumes. That's part of the kinetic molecular theory. But that's actually not the case. So the volumes of gas particles are negligible when compared to the overall volume of the container at relatively low pressure. And that's because they're small and far apart. But what this shows you here is if the volume normally is negligible, if we increase that pressure, the volume that's occupied by the particles is actually pretty significant. And so there is an adjustment. Now, this is not something that you are expected to know. It is not really on the formula sheet, but you may read a prompt or something that talks a little bit about this. So again, at high pressures, gases do not behave ideally. And so this is just a volume adjustment, okay, that you would make. You are not expected to do this kind of calculation. You're just supposed to know what happens, theoretically. The ideal gas law, also the kinetic molecular theory, assumes that there are no forces of attraction between gas particles, but there actually is. If force is proportional, and if you decrease the distance between gas particles by a factor of, let's say, 1/4, the force of attraction actually goes up by a factor of 4,096. So in a relatively low pressure system where gas particles are really far apart, there really aren't any forces of attraction. But in a high pressure system where the molecules are close together, you have to take into account the intermolecular forces of attraction. And those forces are going to be most significant when you have collisions. And so pressure adjustment for gases under high pressure, some good notes for you to keep in your kind of forebrain. When gas particles are close together, the pressure they exert may be less than what the ideal gas law would predict. Neighboring molecules, they exert some forces of attraction when they're close together, and that's going to reduce the pressure resulting from impacts. with the walls of the container. So know what will happen kind of in these extreme conditions. This is kind of a neat picture, right? In a low pressure system, there are no forces of attraction, but in a high pressure system, basically the particles, if something else is pulling, you won't have an elastic collision, and so the velocity will be reduced. There is a mathematical correction, a pressure adjustment for gases under high pressure, so you can kind of see the components of it there. And what the van der Waals equation does is it adjusts for extremes of pressure and low temperature. And so you may see something like this on the AP exam and understand this is PV equals nRT, and then these are the corrections that need to be made at extreme conditions of pressure and temperature when a gas acts less ideally. Looking at low temperatures, ideal gas law assumes that gases experience no intermolecular force of attraction, and at high temperature, those particles are moving really quickly. But at low temperatures, gas particles move slower, they're closer together. So you could get some of those attractions. And so intermolecular forces of attraction are going to increase as the distance between the particles decreases. We have seen this before. So this can lead to condensation at really low temperature or exceptionally high pressure. And this is going to apply to all gases, even gases who have relatively weak intermolecular forces. Condensation can happen rapidly when the temperature of a system drops. So some good notes: kinetic energy is reduced, they move closer together. It can also occur at high pressures for similar reasons. The gas particles are closer together, they experience a higher rate of collision, and some intermolecular forces can cause them to condense. So when a gaseous system is approaching the condensation point, the forces of attraction, the intermolecular forces, are at a maximum. And so these are just some reasons behind deviation from ideal gas behavior. So keep these notes as you look at the concept check, and a lot of it is just theoretical. But again, go back to that first slide where we say, hey, gases don't like high pressure and they don't like low temperature, just like me. And so they're going to behave less ideally. And so kind of understand what happens there. So you can stop on this slide, scan the QR code, tell me that you viewed the video, and if you have any questions, let me know. And then go ahead and complete the concept check in AP Classroom. As always, if you have any questions, just let me know. Thanks, guys.